talk about verifying identities. Yeah, so verify identity. Transform one side of an equation to the other. So our goal is working on one side of the equation, transforming it until we get to the other side. So this is not solving. Make sure everybody's clear. This is not solving, meaning you cannot use all the rules as solving. Like you can't add a number to both sides of the equation. You can't multiply both sides by the same number. You cannot do any of that type of operation. You're only working on one side. Except, I'll give you some cases where you can switch to do both sides. But in general, you only work on one side of the equation. So this is not solving. Everybody clear on that? Okay, so for example, start with a fairly simple one. Secant squared theta times cotangent squared theta minus 1 equals cotangent squared theta. So our goal when we're verifying this is to transform one side until it becomes the other side. And we can use any of the rules we've had for trigonometry. So typically, I'll give you a list of suggestions of methods to use. But for example, anybody have an idea where to start? Yeah. Okay. So converting sine to cosine. Which side are we operating on? Left. Okay. So secant becomes so 1 over cosine squared theta times minus 1. Yes. Notice we're not affecting the other side. Now what? Okay, so we get 1 over sine squared theta minus 1. And now we should be showing all your steps. 1 over sine squared becomes cosecant squared theta. What's cosecant squared theta minus 1? So we get cotangent squared equals cotangent squared theta. So there we verify that one side, if I work on it, I can transform it to the other side. So that would be a completed operation. In general, you like to start, you don't necessarily have to show this on every step, but show what you started at, and then show that at the end you got to what you're trying to get to. Like the rule? Yeah. No, you don't have to. However, it might be in your benefit, so you can keep track of what you're doing. That way, if you have a question in the middle, I can explain what you're doing to somebody else. So, in a way, this is like a proof, where this is your given statement, and this is your proof statement. So you're starting with this and proving that this is true. Now I'm going to give you a list of about 8 suggestions. So note you don't have to use any you don't have to use any of them. However, these are tips that might be useful at certain times. So I'll just call it tips. First one. Start on more complex side. So if you look at this one right here, which side is more complex, left or right? Yeah. Left. Now, think about what you have to do to go from this side to that. It would be a bit messy. I mean, you'd have to start by multiplying maybe by sine squared over sine squared, and then doing stuff. But in general, you want to start on the more complex side. Now, there are some cases where that's not beneficial, but in probably 90% of the cases or more, you want to start on the more complex side. Okay, another common thing, now this isn't always useful, but sometimes it is, change to sines and cosines. So again, that is something that that was done right here, change of sines and cosines. So it's not always helpful. In fact, sometimes it's a hindrance to do so. But it is something that occasionally will be useful. Okay. Another one, look for Pythagorean identities. So again, we look here. We found a Pythagorean identity. Sometimes you have to actually go out and try to find them. Sometimes they just show up. But it's a very useful thing because anytime you see those squares, the squares you often want to deal with Pythagorean identities. Well, let's see which one. Like this one right here, we started off by looking for finding a Pythagorean identity, which was multiplying by this to make one. So here, it's basically I'm just saying look for a way to make one, because those oftentimes are very helpful. You notice on this one, it changed something that was subtraction to something that was just a division problem. Just division is much easier than just subtraction. Let's see, next one on my list, factoring. So factoring is very helpful in a lot of cases. Now some of these are the same as the tips from yesterday. Common denominators. So if you're adding two fractions, or if you have two fractions that are separate, oftentimes in these you want to get them together, get a common denominator. Let's see. And again, like yesterday, I'm going to say the specialized one. Everybody understand what I mean by specialized? This is when we're saying the ones that have, like, pi halves minus theta. Any ones that have pi halves minus theta, we automatically know which rules we're going to use for those, right? Or negative theta. Negative theta. Those are fairly obvious what rule to use. So I call those specialized rules, where they only apply in a very small number of circumstances. Now, sometimes it's useful to separate your numerator. What do I mean by that? Yeah, so if I had, say, 3 plus sine x over cosine x, it might be useful sometimes to change it to 3 over cosine x plus sine x over cosine x. That's what I mean by separate the numerator. Does that rule make sense, or does it make sense how I did that? Okay. And let's see, what's this? I think I have 2 more on here. Work both sides to a common middle. So you can work on both sides of one of these identities. However, you cannot work it as an equation. So if we were looking at this one here, maybe at the beginning you saw this, and I'm going to change this into just sine and cosine. Sine theta over cosine, or sine squared over cosine squared theta. Now, I could work this one down until I get the same thing I got on this side. Typically, it's easier to just stay on one side and stick with that. However, sometimes if both sides are fairly complex, you might want to simplify one side, simplify the other, and then try to work them towards the middle. Does that make sense? So remember, you are not solving, you are not multiplying, like on this one, you are not multiplying by cosine each square in each side. That would not be an allowed option. We cannot do that. We can operate on a single side, operate on the other side, until we get to the same answer. And the last one I'm going to put on here. Reservations. So I'm going to show you an example of what I mean by reservations with the next one we're doing here. Cotangent squared theta, cosecant squared theta, minus cotangent squared theta equals cotangent to the fourth theta. So which side do you want to start working on? Left is probably going to be easiest. And what do you see first to do this? Okay, simplify the sine and cosine. Probably don't want to do that with this one. Because there's a more obvious step. Factor. Cotangent squared theta times cosecant squared theta minus 1. Now, I know on the side I need cotangent to the fourth. I have two of them already. So I'm going to reserve this one and not even touch it. That's what I mean by reservation. If I get part of what's on the other side, I'm going to just say I'm done with that and not even look at that anymore. You understand what I mean by that? So for example, I could rewrite this as cotangent squared theta, cotangent squared theta, and I've already got this part taken care of. I'm going to reserve this cotangent squared right here to match with this one here, which means I just have to get this part to equal that part, which it clearly does because of the Pythagorean identity. But this is what I mean when I talk about reserve. And most of the time when I'm doing this, it's going to be more complex ones where it's not, may not be as obvious. But it's just see if there's something that matches on both sides and take that out and then look at what's left over. Everybody clear what I mean by that? Okay. So we're going to do a few more of these verifying identities. Some more complex, some simpler. Okay, how are we going to verify it? Okay. Okay. So you can work on either side. It doesn't really matter. If you think the right side is a bit more complex, so that might be what you're looking at. Is there anything that you would reserve that's the same on both sides? Yeah. So we already have a common denominator here. So I'm just going to reserve that and say, I don't even have to touch the denominator. I just have to work in the numerator only. So all I have to do is show that tangent squared equals secant squared x minus 1. Is that true? Yes. By what rule? Okay, so I can just immediately say tangent squared x is over 1 plus secant x is equal to tangent squared x over 1 plus secant x. One step. Some of them are going to be one step, some of them are more than that. And just keep track, what method did you use? Here we use the Pythagorean identity. Okay, a bit more complex one here. 2 plus cosecant theta times secant theta over cosecant theta secant theta is equal to sine theta plus cosine theta squared.
Is it possible to cancel out cosecant?
Okay, in what way?
On the left.
So you mean just doing this?
Yeah, so this one is possible.
You can't just do it in that form, no. However, we could separate the numerator into the two parts and do that. So which side is more complex? Okay, left is probably more complex. However, in this case, I'd probably start working on the right. Because of the squares. I tell which side to start on? It actually doesn't matter. I generally don't like even trying to get squares. However, it is completely fine to do so. So we could start on left or right with this one. So let's start on the left, like you're suggesting. What do you think here? Or what can you see you can do? Okay, so separate it. So we have 2 over cosecant x plus 1. Okay, then what? Okay, so this becomes 2 cosine x sine x plus 1. This is the reason I would probably start on the other side. Is think about what we need. We need to have a sine plus a cosine squared. What do we do? What can we change that 1 into? Yeah. So I can change it to 2 cosine x sine x plus sine squared x plus cosine squared x. That is a very not obvious move, right? Oh, what is sine squared plus cosine squared? 1. Therefore, I can change this 1 and use sine squared plus cosine squared. So, but that step is not obvious. In fact, it's very counterintuitive, right? Because it seems to make it more complex. Well, the problem is we don't have anything to reserve that matches the other side. But now, what can we do to factor this? Okay, I'm going to rewrite this as sine squared x plus 2 cosine x sine x plus cosine squared x. What does this look like? Like an a squared plus 2ab plus b squared. What is this going to factor? Sine x, so sine x plus cosine x squared. Now, if we start at the other side, so let's just look at it if we start at the other side. This one actually might be a good candidate to work both sides. Okay, what will we get if we multiply this out? We get sine squared x plus 2 sine x cosine x plus cosine squared x. And then we have sine squared plus cosine squared. That's our protagonist identity we look for. You get 1 plus 2 sine x cosine x. So now, again, the next step from here is not an obvious step. However, notice we got from here, we got the same thing here. So this might be a good one to say we're going to work both sides. You follow what I mean? So sometimes if you have one that's reasonably complex on both sides, that's what you want to do. Like this one, we simplified it to a point where we're not clear what we're going to do next. This one, we simplify it, and here it's not clear what we're going to do next. And notice, but these two are the same steps, right? Therefore, we would actually be finished at this point. Well, if you were doing it this way, this whole thing is the answer. Everything you see on the board. The work is the answer. So remember, it's like a proof. You're trying to show from one step to the end and the reason. This one, we're just showing we can get from one step to the end. So I could start here, and I know the next step after this would be here. The next step after this would be here. And notice, that's what we did over on this side. We just went all the way with one side without going to the other.
So in this case, you have to replace that?
Oh, well, no, on this step, I said, it's not obvious that we need to do this, to get from that to this. It's not an obvious step to do that. However, since I knew I needed sine and cosine squared, I knew I wanted to do that. So it's not clear why you might want to do that. That's what I'm saying is, some steps are not going to be obvious. And that's probably one of the biggest examples of non-obvious steps. Let's see, I think I want to do one more here and then time to work. So sine theta over sine theta plus cosine theta is equal to tangent theta over 1 plus tangent theta. What do you think? Okay, so change sine to cosine to tangent theta? Oh, okay, change tangent theta to sine to cosine. Okay, so equals sine theta over cosine theta over 1 plus sine theta over cosine theta.
I was talking about working the left side.
Oh, okay. So I'm not sure, what do you mean by changing tangent theta?
Well, on the left side of the equation, you have sine theta over cosine.
No, you don't. You have sine over sine plus cosine. You can't do that at all. Because you can't separate the denominator, you can separate the numerator. So, in case you're in doubt, tangent is usually more complex than sine and cosine. And so if you're starting on more complex side, definitely going to be the right-hand side. But notice, when we're trying to get to have only sine and cosine, which means we definitely want to change everything to just sine and cosine.
So you can change, instead of that, your finger, that is it, you can change the tangent to, I got them the tangent.
Okay? So, definitely, I'll say you definitely want to work this side. Because now we've only got sines and cosines here. We start with cosine, or our goal is sines and cosines. So now what? Let's see. Let's start looking through the list. Start on the more complex side. Check. Change the sines and cosines. Check. Look for Pythagorean identities. Okay. We could multiply, like for example, at the bottom, maybe we could do multiply by, instead of changing sine and cosine here, is 1 minus tangent theta. That might be an idea. Multiply that top and bottom. And that could get where, that's where we want. So that's something to consider. Probably not what we want to do yet, but if we get stumped, there's an idea. Factoring. Is there anything we can factor? Common denominator. Do you have anything to get common denominator of? Yes? What can we get a common denominator of?
We only have one fraction.
Yeah.
We can separate the denominators.
Oh, there's no numerators we can separate. Oh, get a common denominator between these two. So we have sine theta over cosine theta on top over cosine theta over cosine theta plus sine theta over cosine theta. And since we got a common denominator, I'm just going to write it as cosine theta plus sine theta over cosine theta. Okay, now what? Okay? How do you divide a fraction? Flip and multiply. So we're going to take the bottom and flip it, multiply times the top. Sine theta over cosine theta times cosine theta plus cosine theta on top. And on the bottom, yeah, cosine theta plus sine theta.
Then you can cancel them.
Cosine cancels, which leaves us sine theta over cosine theta plus sine theta, which is what we're trying to get to.